In today's video, we will consider power series. These lead to the most effective applications of series. To get an insight, let us consider the well-known series, namely the geometric series. We recall that 1 over 1 minus x was the sum of x to the n, starting from 0 to infinity, once absolute x was strictly less than 1, otherwise the series would be divergent. Okay. Now, this actually says that the function 1 over 1 minus x can be written as an infinitely long polynomial. Well, these are called power series. Okay, so we can define directly. By this, I mean, forget 1 over 1 minus x. We can define directly a function in this form. Okay, this function would not be 1 over 1 minus x function, actually, because its domain would be restricted. So it would be defined on the open interval minus 1, 1 into reals. Now, this tells us that if we replace the sum of the powers of x up to infinity by a standard polynomial, but which does not stop, continues up to infinity, we would reach the following thing. Okay, we could consider then, okay, let me say an infinite polynomial namely a0 plus a1x plus a2x squared, and it continues up to infinity. Okay, note that we could show this in this form. Now, this series will be convergent sometimes, okay, for some x, possibly, and for some other x's, it would be divergent. So the domain of a function defined by such an infinite sum, okay, could differ depending basically on the coefficients an. Okay. So our formal definition would be the following. A formal series of the form for some fixed is called a power series. Okay, why do we introduce this x0? The role will be clear in a minute, okay? Namely, the convergence of such a series will be symmetric around the point x0, as we will see quite soon. Let me extend the definition a little bit. The set of values, actually the set of x's, such that, okay, the power series converges is called the interval of convergence. For the power series. Since it's always an interval. Okay. Now, this interval of convergence, that is, the set of all x's so that the power series converge, is never empty. Namely, okay, for any power series, okay, of the given form, okay, the series converges if x is equal to x0. So, x0 belongs to the interval of convergence for the power series. So at least we have one point there all the time. Now, which other x's will be there? Now, this is summarized in a rather long theorem that I will state now. Okay? I will call this the main theorem. For power series. We will not be in a position to prove it, but we will try to understand what it really says. So let a power series be given. Okay. Then exactly one of the following occurs. Okay. Firstly, okay, there exists a positive real number such that the power series converges, in fact, absolutely. Okay. For every x in the interval x0 minus r, x0 plus r. Okay. So we see that the convergence happens in a symmetric way around x0. So it will become an interval anyway. And diverge, okay, for every x, not in the complement, but in the complement of the closed interval here. Now, if we write f of x equal to this infinite sum, then this function is differentiable. Okay. Okay. For every point in this interval. And moreover, the derivative function can be written as the sum n1 to infinity an times nx minus x0 to the n minus 1. Well, actually, if you consider the long version of the sum, it means that you are calculating the derivatives term by term. This is, of course, when n is 1, okay, a1, okay, just that, a2, and in the second term, okay, when n is 2, you have twice x minus x0, and it continues like that. You have a3, 3 times x minus x0 squared, etc., which is, by the way, the sum 1 to infinity of an times the derivative of x minus x0 to b. This is termwise differentiation. Now, not only that, okay, we can even integrate this function. Well, this is natural because if it's differentiable, it must be a continuous function, so it must have an integral. Let us state that more precisely. Now, for any interval AB contained in the open interval, okay, one has the integral of this function is the integral of the power series okay. Now the point is, it can be done term by term. So it is actually the sum of the integral of x minus x0 to the n dx. Of course, we can calculate this very easily. So the important thing is that termwise integration is valid. Okay. Well, these two properties of termwise integration and termwise differentiation will lead to very nice consequences. Now, this is for the case A. For the case B, okay, I mean, there may not be such an R, but it may happen that the series converges for every x in R. For every real number, we have a convergent series, okay? And in this case, also, termwise integration and differentiation are valid. And finally, the third case happens that the series diverges for every x, okay, such that x is different from x0. Of course, when x is equal to x0, the power series, as we already stated, converges. Okay. Now, this tells us, actually, if you look at the conditions, the three conditions, they are disjoint. And the most important thing is the first one, actually. Okay? That is, we have an R and so on. Now, let us state some definitions here. Okay, let me say definitions and remarks. Well, firstly, okay, in part A of the theorem, we have a real number. Okay. This real number R tells us that we can go away from x0 by a distance of R. Okay, it's a positive number. And in that interval, we have convergence. Now, if we go outside that interval, okay, except for the endpoints, we have divergence. So it limits the values of x in an interval where we have convergence. So, okay, in part A, we have the following. We have our x0. We can go as far as x0 minus r, respectively x0 plus r. And in this interval, okay, the series, okay, so let me write it over here. Okay. Here, series is convergent for every x there. And if we forget the endpoint and continue this way, okay, the series is divergent because then the distance of x to x0 is outside this closed interval, so it is not in there. And similarly here, we have divergence of the series. So R here tells us the boundary, how far x can go away from x0. Okay. Now, okay, we say, that's our definition, R is the radius of convergence. Well, it's called a radius because historically and practically, power series are defined for complex variables. And such a distance formulation in complex numbers gives us a circle. And R becomes its radius, but that's not our concern right away. Okay. Now, we extend this definition. Similarly, we say in part B, okay, R equal to infinity is the radius of convergence. Okay. And in part C, we put R0 is the radius of convergence. So, for every power series, there is a radius of convergence. In the first part, that R is this one. In the second part, R is infinity because x can go as far away from x0 as we want. And finally, in C, Okay, it cannot go any further. Okay. So this is our definition of radius of convergence. Its second observation is that, okay, in parts A and B, okay, the derivative and the integral, okay, to regard the integral as a function, okay, we evaluated x0 to t, okay, f of x dx, where x0 t lies inside of x0 minus r, x0 plus r. In part A, in B, it doesn't matter. Okay? Also have, okay, a power series representation. Okay. This is clear from the term-by-term integration and differentiation. Now, this happens to have, which can be shown quite easily, the same radius of convergence. Okay. But the interval of convergence may change. Okay. This is because, okay, I will say it as a third observation. Okay. Now in part A, we see that the theorem says nothing about the endpoints. It says something about the open interval inside and the open interval outside. But for the endpoints, it tells us nothing. So the theorem says nothing, of course, in part A, about convergence when x is x0 minus r or x is x0 plus r. So, okay, convergence at these endpoints must be checked. Okay, separately. Okay, this is one point we will see in the examples quite directly. Okay, let us see some examples. Okay, the question is to find the radius of convergence R and the interval of convergence I for the given series. Below. Okay. Now our first example will be the series, actually starting from 1, minus 1 to the n over n. Oh, sorry. X to the n. Okay. Now, clearly, this is a power series. X0 is 0. Okay. And we want to determine when this series is convergent. Note that we regard x as a constant here. It's a given number, okay? And when is such a series convergent? Of course, when we look at this series, we observe that we have x to the n and exponential growth. So we think to use, okay, the root ratio tests. Okay. But of course, we do not know if x to the n, that is, x is positive all the time. Hence, x to the n can be negative. For example, if x is minus 1, well, we won't have a positive series. So we cannot use the root ratio tests directly. Okay. So since x to the n can be negative or positive infinitely many times, okay, we apply our tests to the absolute value. Okay. Now the general term is non-negative, so we can apply it. Okay, say, okay, we have chosen to use the root test. Ratio test is just as well. Here, it can be applied directly. So then, we have x to the n over n. We take the nth root. Well, this is absolute x divided by n to the 1 over n. Now, using L'Hopital's rule applied to x to the 1 over x, we see that this approaches absolute x when n goes to infinity. Okay. Now, the root test tells us that if the limit of the nth root of the general term here, okay, is strictly less than 1, the series will be convergent. If it's strictly bigger than 1, the series will be divergent. So, by root test, the series absolute value x to the n over n is convergent if the limit is strictly less than 1, and it is divergent if x is greater than. Okay, here we have one little problem, namely, because of the first condition, that is, if absolute x is strictly less than 1, then we have convergence with absolute value. Well, this implies, of course, absolute convergence for the original series. So, if absolute x is less than 1, then the series is, in fact, absolutely, but whatever, it's convergent. Fine. Okay. But if the absolute value of a series in this form, okay, diverges, we are not sure that without the absolute value, it also diverges. So let us have the following very important remark here. In general, if the series diverges, then the series, okay, can be convergent. Okay, as in conditionally convergent series. Okay. For a conditionally convergent series, the series is convergent. With absolute value, it is divergent. Okay. So we cannot say that if this is divergent, this one is also divergent. Okay. The big but comes here. But if divergence of this series, okay, is by root or ratio tests, then the series without absolute value is also divergent. Because okay. Now, let us recall what the root ratio tests did. They compared the given series with a geometric series. Okay, to compare a series with a geometric series and say that it is divergent means exactly the following. Okay. It means that we are comparing AN, actually absolute AN, with some geometric series. Perhaps some say R to the n, which happens to be positive. Okay? And to say this one is divergent, okay, we must have the geometric series divergent, if that comparison works. Okay. So here, okay, comparison is done. So it says that R is bigger than 1. Otherwise, okay, well, you can even put this here. Okay. If R is strictly less than 1, of course, this inequality would not say this one is divergent. So we must have R bigger than 1. Okay. Actually, it's strict anyway, so we don't care about that much. It could be equal to 1. Now, this comparison, of course, tells us that Rn goes to infinity with n, because R is bigger than 1. So, absolute AN goes to infinity with n. Okay. Like from this comparison. Now it's clear that limit of AN cannot be 0. Because if limit of an were 0, limit of absolute an would be 0, but it's not. So, okay, the series an diverge, okay, because the limit is not 0. So, by nth term test. In short, okay, if a series with absolute value diverges, you can't say anything about the series without the absolute value. But if the reason is root or ratio tests, you can say it. Okay. So continuing our discussion, okay, hence we get if absolute x is greater than 1, then the series without absolute value, that is x to the n over n, is divergent. Okay. From the remark above. Okay, so we have the following situation. Here we have 0, that's our x0. Okay. If absolute x is bigger than 1, so if we move this way or this way, we have divergence. If absolute x is less than 1, here we have convergence. But this precisely says R is 1. Now, to finish our analysis, note that we did not yet check the endpoints. Okay. Now to find I, okay, we already know the following. I is the interval minus 1, 1. Okay. Possibly, okay, with some endpoints. Okay. So, okay, we check the endpoints. What are the endpoints? Of course, 1 and minus 1. In the first case, when x is minus 1, okay, the series becomes the following. We know that this series is convergent. Namely, okay, it's alternating, and 1 over n decreases to 0, so convergent by alternating series test. Okay. Now this says minus 1 is an I. On the other hand, if x is 1, we have the series 1 over n, harmonic series, it's divergent. So 1 is not big. Okay. Conclusion, I is the closed minus 1, open 1. Okay. Now let us see that this endpoint property, that is, whether the endpoint belongs to the interval of convergence or not, depends on an quite heavily. Okay. But before we pass to the next example, let us continue this example by considering the derivative. Okay. Okay, this is clearly n1 to infinity, the derivative of x to the n over n. Okay. We know it has the same radius of convergence. So, okay, let us calculate that. This would be the sum of nx to the n minus 1 over n. Okay. Now, radius is the same as that of f. Okay, by theory. But we can show this quite easily as well. So, r is 1, as in the previous case. But, okay, consider the endpoints. In this case, we have the sum of now n1 to infinity, okay, minus 1 to the n minus 1. Well, clearly this is divergent. Okay. Because minus 1 to the n, or n minus 1, okay, does not have a limit in the first place, hence its limit is not 0. So by nth term test, it diverges. If x is 1, we get the sum of 1's, which of course, again, is divergent by nth term test, which says that now the interval is just the open interval without any endpoints. So when we differentiate, the endpoints may not continue to belong to the interval of convergence here. Let us consider now a second example. Okay. Say we have the series 1 to infinity, 1 over n squared, x minus 1 to the n. Now, this is a nice power series, okay? As we did before, okay, we apply, okay, this time for a change, ratio test. Of course, we apply it to the absolute value. Okay? Now, the ratio test says that you look at the ratio of the absolute value, but clearly, if x is 1, okay, you cannot divide by 0. So we have to take that point out. 1 certainly belongs to the interval of convergence. It will not pose a problem. So assume x is not 1. We have then the ratio 1 over n plus 1 squared, x minus 1 to the n plus 1 in absolute value divided by 1 over n squared, x minus 1 to the n in absolute value. Well, that is exactly n squared over n plus 1 squared times x minus 1. Now, in the ratio test, you look at the ratio and let n go to infinity, so we get x minus 1. Okay. So series converge if the limit value is less than 1 and diverge if the limit value is greater than 1. Now this tells us, as before, that the radius is 1. Okay. So we have the following diagram again. 1 is the center point. Okay. We can go far away 1 by 1 unit up to 2 or up to 0. Here we have x minus 1 less than 1, so convergent. And outside, okay, x minus 1 is bigger than 1, so divergent. Okay. This says that R is 1. Now for the endpoints, if x is 0, okay, we consider our series, okay, which was 1 over n squared, x minus 1 to the n. Well, this is certainly 1 to infinity, minus 1 to the n over n squared. Now, this series is clearly convergent by alternating series test, or okay, look at the absolute value. You have 1 over n squared, okay, or okay, taking absolute value, we have 1 over n squared. Okay, p is greater than 1, so convergent. Okay, and by absolute convergence theorem, also the series is convergent. So you have many ways to show that it is convergent. Okay. If x is 2, the other endpoint, you have the series 2 minus 1 to the n over n squared. Well, this, of course, is the p series itself. It's convergent. All this says that the interval of convergence is the closed interval 0, 2. Both endpoints are included here. Okay. Well, still a third example. This time, consider the series. Say n starts from 0 to infinity, x to the n over n factorial. Now, this series, again, is not positive because of x to the n. So, okay, we have powers, but we have factorial here. Now, note that once we have factorials in our series, we prefer to use the ratio test, not the root test. since there is n factorial. Okay. So we look at the ratio, that is x to the n plus 1 divided by n plus 1 factorial divided by x to the n over n factorial, of course, as before. Okay. We cannot apply the ratio test if we don't know positivity, so we make it positive. Secondly, if x is 0, we cannot divide by it. So assume it is not 0. Now then, the rest tells us that we have absolute x divided by factorial simplification, n plus 1. The limit when n goes to infinity is 0 for every x. It does not depend on x. Then this is less than 1 for every x. So converge for all x. Okay. We have part B case in the theorem. This tells us that the radius is infinity and the interval is all of R. Durduk. Aslında şöyle yapalım. Bir dakika. Okay. Now consider the following example. We have here n, okay, 1 to infinity, say, n to the n, x minus 3 to the n. Now this is, of course, again, a power series, okay? Because of n to the n, we may prefer to use the root test instead of the ratio test. So use root test. Of course, for the series, absolute n to the n, x minus 3 to the n. Thus, okay, here, the nth root of the general term will become n x minus 3, of course, in absolute value. Now, this limit, when n goes to infinity, clearly is infinity. If, okay, x is not 3. And if x is 3, then we have 0 here, so this n does not matter. It is 0 all the time. So here n goes to infinity. Clearly, in the first case, this is greater than 1. Here, it's less than 1. So, by root test, the series n to the n x minus 3 to the n with absolute value diverge for all x different from 3, and of course converge if x is 3. Okay. Now, by our previous remark, 2 examples before, okay, the same is true without absolute value because we use the root test. Okay, since the divergence is a consequence of the root test, recall, it meant that the same result is true without absolute value. So, also, okay, the series without absolute value, okay, is convergent only for x equal to 3. Okay. This is the part C in our case, in the theorem. So we conclude R is 0. Okay. You cannot go away from 3 at all for convergence. And finally, the interval of convergence is just the point 3. Okay. Anywhere else, you have divergence. Okay. Now, a last example on finding radii and intervals of convergence. Consider the series, okay, say x minus, or just x to the 2n, divided by 2 to the n plus 1, and starting from 0 to infinity. Okay. Right. Okay, this is a nice enough power series again. Note that we only have even powers of x. Okay, let us see what this changes. Okay. Well, as before, okay, we use, because of this plus, okay, a root of a sum is not a nice expression, so we prefer, okay, ratio test. Since, okay, it can be managed, but, okay, this is a little bit problematic. Okay. So instead, we use the ratio test. Well, we look at the ratio, x to the 2n plus 1 divided by 2 to the n plus 1 divided by x to the 2n over 2 to the n plus 1. Now, because of the even power, we already have positive terms. Okay. Of course, x must be different from 0 again. So let me put here for x not 0. Okay, I don't have to put absolute value. Directly I can check the ratio test because everything is positive. Now, this is x squared divided by, okay, 2 to the n plus 1 divided by this term, or if you want, this one. Okay. Now, the limit here is clearly 2 when n goes to infinity. You can easily check that. So the limit becomes x squared over 2. Now, by root test, okay, if x squared over 2 is less than 1, series converges. If x squared over 2 is bigger than 1, series diverges. Okay. Now, what does all this mean? It means the following diagram. We have 0, okay, and x squared less than 2 means that absolute x is less than square root of 2. So we can go as far as square root of 2. And outside, we have divergence. Inside, we have convergence. Now, this by definition says that R is square root of 2. Because just consider the second one. X squared is bigger than 2 means absolute x is bigger than square root of 2. That is, we are outside, we have divergence. So the radius is root 2. For the interval, we check endpoints. if x is minus root 2, actually it doesn't matter, so I will just write plus minus root 2. I will consider both directly. The series becomes this one, okay, which is precisely the series 2 to the n divided by 2 to the n plus 1, which of course diverges by nth term test. Okay, so the interval of convergence is the open interval minus root 2 plus root 2.